Hey everybody, today's project is a addition on my AVID CNC of this Deutronics probe. I've wanted a touch probe for a while. When I started adding the rapid change ATC, I realized I didn't really want to keep my touch plate as a height finder so much for my workpiece. I really wanted to use it as a touch-off tool for the ATC, and a touch probe would let me do some things that I really want to do, like be able to find the center of holes on the inside of like a hole or a square cutout, as well as find the center of an object from its outside edges. And so none of that I can do with the AVID probe because that's a conductive probe, so it has to be done between something like a bit that's in the collet to the top of the workpiece on the touch plate. So I looked around for some different probes, and this one from Deutronics is really nicely built. It does X, Y, and Z, and it has adjustment for concentricity or run out. So it can be used in the chuck or in a fixed location. What I decided to do is I wanted to use it in the chuck, so I have the wire that can reach it while it's in the chuck or the collet. But I also want to be able to use it with the laser. And the other thing is, this is a normally closed probe, so to use it in parallel with my AVID touch plate, I need to have this in the inactive state normally. So I have two choices for that. I can leave the probe up here somewhere and have the wire plugged in, because this probe in its idle state provides a short circuit which keeps it inactive. Or you can make a little probe, or a little shorting block, so I have this where I can disable it by doing that. But what I decided was I wanted to be able to use it for my laser as well. So I made this little mount out of some they're 80-20 hinges and a few little blocks I made. So essentially this ends up being the storage place for my probe, as well as the second use place for it. So I can just put it up here out of the way like this. It's right next to my laser mount here, so it doesn't interfere with that. But then when I want to use it as a probe, it goes up tight in here to a fixed repeatable location, so I can just tighten that down and then come down and probe with it as well. And it's a little bit, it's about an inch lower than when my laser's on here, so it sticks down well. I can use that to set my Z height for the laser. And I could actually do X and Y as well, but I don't have a hard stop that makes it repeatable in here yet, so it's kind of useless for X and Y yet, but I'll fix that in the short order. But this video is really how do you hook it up electrically and use it. The software I'm going to save for the future. I have a whole probing screen in mind that I want to write, because I don't really like any of the probing windows or features in different screens that I have. I mean, there's parts of the AVID one I like. There's parts of the one in the WX4 screen set that comes with Mach 4 that I like, but there's nothing that has everything that I want. So I'm going to write my own, and I'll have a follow-up video for that. But this is just about how to get this probe to work.
All right, I wrote this document to help explain how the current AVID touch probe system works, as well as how we're going to add a normally closed touch probe. And it's also captures all the part numbers and links to Amazon and other places where I got the components. So I will post this in my Google Drive, and I'll put the link in the description section in the video below, so you can go download this and use it if you like. So we're just going to go through this couple of the schematics and stuff on this document and use it as a reference for the description. Well, let's just go to the schematic page here and get into how the existing AVID probe circuit works. So everything in this box on the right is what is there on your machine, except for this one wire, and I'll explain that a little bit later. Then everything over on the left dashed box is what's inside the probe itself for this particular probe. So there's an indicator, LED, and then basically 3 switches. And this little section in the middle is the circuit we have to add to kind of marry these two together and make them work together. So let's start on the right. So on the right we have the AVID probe system. This wire here is the body of the touch plate probe, and the one red wire here, and you can see the little magnet, that's your magnet wire that gets attached to, you know, your spindle collet or your bit in the collet. And so those are the two components that you see. What's back in the ESS is an opto-isolator here. It's actually not on the ESS, it's on the CRP 850 board, where this is an isolation between the 12-volt domain that's used for external sensors and things and the 5-volt domain that the ESS runs on. One of the things that's about a CNC is the motors and the relays and actuators, different things can be very noisy electrically. So generally you try to keep the electrical power domains isolated, because you don't want your controller, the ESS card, to get a lot of noise in it. It could start having malfunctions and not work properly. So those power domains are generally isolated with opto-isolators or relays or other things. So that's how this is being done here. So basically what happens when you have your magnet attached to your bit and you're lowering your spindle down to do a probe touch on this, eventually the bit comes down and makes contact with the plate, and so basically you're shorting these two wires together. So just ignore these ones off to the left because they don't exist in this part of the description. So you make contact here, and so what that does is the 12-volt supply is providing a voltage to the top of this isolator through this current limiting resistor. This resistor is only there to control the maximum amount of current that can go through this diode, because it can only take probably 10 to 20 milliamps or so. And so that completes the circuit, and you've got current that is basically just running down through here to the 12-volt ground. And so what that does is create, once you have current in this photo diode, it emits light inside the package over to a phototransistor, and that turns this on. So this essentially is a switch that when it's turned on, now this is shorted, and I'm not showing the rest of this, but essentially this is providing a connection or an indication to one of the inputs on the ESS that is set up in Mach 4 as a probe pin. So while you're doing a probe routine, say typically use like a G31 probe command, or the probe routine will, it does a move and it's just sitting there waiting for the signal to trigger. So it's inactive and it's moving in the Z or X or Y direction, and all of a sudden it sees this signal transition to active, and it stops immediately, and then it records those coordinates, and that's how the probe routines work. So this is what's called a normally open circuit. As you can see, this gap here, the inactive state is when that's open, and when it's shorted together, that activates it. So that's a very easy circuit to build because it's just a simple electrical connection, as you see here. The problem with it is it's kind of error prone, or it can be less reliable, because just think about, like, if there's a little bit of dirt on this probe plate, like you got some sawdust on there and maybe you don't make electrical contact, then your spindle will keep coming down, and if there's no good electrical connection here, it'll keep going and it can jam into that plate. It can break your bit, for example. If this wire is broken, like what's happened to me several times, is this little end of the wire where it attaches to the magnet, that can get fatigued from bending it so many times when you're trying to pull it off of the spindle, that the wires can crack inside and it creates an open circuit. Well, if there's an open circuit in there and you don't know it, then this circuit can never be closed, because even though it closes here where the bit touches the plate, you still have an open in here and it won't make contact. So again, there's no way for the probing routine is going to check to make sure that it's not active before it starts. So if you were to touch this magnet to the plate and then hit the probing routine, you get an error right away. But the converse is not true. It can't tell if there's an open circuit here because open is the normal state. So this isn't very reliable. There's no way to tell if the whole circuit path is good before it starts. And that's why people don't like the normally open circuits as much, is because they're just not reliable that way. And open is the more prevalent type of defect that you'll see. So, but again, there's benefits to these. I mean, obviously it doesn't take any fancy switches or hardware to make these. So, and they're very accurate and everything when they're working. So that's how that works over here. Now, if we go over to the left side, we have this normally closed probe, and this is pretty typical of a touch probe, or sometimes they're called 3D probes. And then, so a probe or a 3D probe is something like the picture shows here, where you mount this in your collet, and then the probe sticks down, and so you probe down with that. And this can probe left or right or forward or back or up and down. So that's why it's 3D. It's basically a little disc in there with 3 switches, each at 120 degrees from each other. So it's kind of a little disc that's perpendicular to this needle in here. And so if that needle is rocked sideways or lifted up, it will make at least one of these switches open. So that's why it's called a normally closed probe, because in its idle state or inactive state, all these switches are closed. And so this is the coaxial connector that's shown right here on the side. That's a short circuit all the way through. So when it's inactive, you have a current path right through all the way around. So it's inactive, and because that's a short, there's no voltage across this, and so your diode right here is not lit up. So that's how it works. And then once it's opened, the voltage that's present here needs to be detected over here, but it also provides a current path now. Once one of these switches are open, no longer can the current go this way, and so now the current will go through the connector and down through the diode and around. So you'll get this diode's going to light up, and that's the little indicator. It's actually, you can't see it, it's over on the side on this one, but it lights up there. And again, this 10K ohm resistor here, its purpose is to limit the current for this diode, as well as, just like I talked about over on the opto isolator circuit. Light emitting diodes are current controlled devices, and they can't have they have a small range of current. It takes a certain amount of current to make them light up, and then they can only take so much current before they burn out and get destroyed. So they almost always have to come with some kind of a current limiting resistor. So basically, we have a device over here that's normally a short circuit, that when it's activated is open, and we have a device and circuit over here that's open normally and then gets shorted. And so they're incompatible by themselves, because if we simply hooked up this probe to this, we would always get a probe condition, because this probe would short out these two lines. So what we need is a circuit that inverts the normally closed, so that when it opens, it actually closes the circuit over here. And so this little board in the middle here is an open driver circuit, and what it is a switch, which is just a simple FET transistor in this case. And the switch is either on, which when it turns on, it's essentially closing the switch here, and so it creates a short between this pin 2 up here and this pin 2 on this other connector over here. So it's a one-way switch essentially. It's either open or it's closed, and it's controlled by on this side, and it also has an LED indicator, so it lights up when you provide a on voltage here. And so when you turn this voltage on here, it's the current goes down through the diode and resistor and lights up the diode, and the voltage is present here. There's really no current. A field effect transistor is essentially a zero current. It's a voltage controlled device. There's no current in here, but the voltage that's here turns this device on. And they also have another resistor on this board, this 1K ohm resistor, to provide a little bit of a load and pull down to keep it inactive. I don't need that because this probe here, that it's as strong as a pull down as you can get because it's a short circuit. So this is not needed in this case, and I don't want it because I don't want the extra current draw on that, and you'll see why in a bit. So I actually take this resistor off. I just took a needle nose plier and crushed it, but you can unsolder it too if you want, but we don't need that in there. So I took that off. So what we have here is we bring a wire from the 12 volt power supply inside the AVID control box, and we run it through a 2.4 k ohm resistor to the input of this. And the purpose of this is when the normally closed probe gets opened, we need to provide a positive voltage on this terminal to turn this transistor on so that it can short out these two wires. And so this probe doesn't have any voltage of its own. So the other thing is we want to provide some power to light this diode up. So the 2.4 k ohm resistance is sized so that we don't have, there's a couple of things we have to look out for. We want these LEDs to all light up when they should. We don't want to burn these switches out. These are very small, tiny little contacts with ball bearings on each side of them, and so the specification from the probe, for this particular probe, is that they shouldn't have more than 5 milliamps going through these when they're closed, because basically, too much current can cause them to get kind of damaged on the edges. They'll arc a little bit and stuff. So you want to keep the current through there under 5 milliamps. So I sized this resistor here to say, so basically you have 12 volts through 2.4K going through that. You get 5 milliamps. So I took it right to the maximum that the switches could take. So the switches make this, pull this voltage down to ground, and so the switch is off because the voltage is lower than the threshold voltage of the transistor. And because the voltage is 0 across this, the voltage across this diode is 0, so the probe does not light up, and neither does the open driver diode because that's got 0 volts on it. So essentially it's low, which means this resistor or transistor is turned off, so it does not activate this circuit. So now if somebody pushed on this needle, it's going to open up one of these, and there's no longer a grounding path through there. So now instead of coming down through these, it's actually going to provide a couple of current paths. So we get we get this one here that's going to come down and come up through here and down through this because these are open again. So it's going to light this one up, and then we're also going to get the current going down this path and lighting this diode up, and we're going to get voltage on the gate of this transistor. So we're turning both LEDs on and we're energizing the transistor, and essentially you've got these two parallel paths here with the 1K, and the 10K over here is kind of insignificant. So this 1K resistor is kind of what sets the voltage, that and the voltage drop across here. I was measuring about 6 volts on this because it's essentially a voltage divider between the 2.4K and the voltage drop across this. So 6 volts is more than enough. It only takes a few volts to turn this transistor on. So that turns this transistor on, turns all the indicators on. And with this transistor being on, it's now a short circuit itself. And so we are creating a current path. Oops. Misdrew that. A current path through here, through the transistor and down. So that's essentially the same thing as a short here that you would get with the touch probe. So that's how it works. So you basically are taking the normally closed probe and turning that into a normally open output. And then when the probe opens, it's turning into a shorted output so that it's compatible at this point. So you can hook multiple probes to this because of this, because they're all in parallel. So basically, you could have a touch probe, you could have a tool setter, and you could have this AVID probe all hanging on your machine at once, and any one of them can cause a short here and trip the ESS to think that there's an active probe. And that's the way I plan to use it. I'm going to leave my ESS or my AVID touch plate in a fixed position on my spoil board and use it as a tool setter for my ATC, and maybe sometimes I'll take it out and use it to probe electrically my spindle bits. But I can also put this probe in my collet, or I can have it sitting up next to my laser, and I don't have to turn it on or do anything. I can just flip it down into position and probe with it, and it will also trip the circuit. So you can seamlessly use them in parallel at the same time. So that's basically how it works. So this is the link to the Deutronics probe, and this circuit essentially is going to work with any kind of normally closed probe. And then this is a little board I bought off of Amazon. There's also other circuits it's anything that would be an open drain type pull down switch like this. You could use a relay as well. It would need to be a buffered relay, because a normal relay would draw too much current to work with this exact circuit. But this is solid state, so it's it's not going to wear out or anything, and it works for small signals. So I would recommend the solid state route. The last thing I wanted to point out was on this page was this chassis wire connection here. So a lot of people have asked me on my videos, why don't I have the magnet wire ever mounted or stuck on my collet or my bits when I'm probing? They see me just probing with it and the magnet wire is off laying to the side or whatever, or sometimes it's sticking on my rotary axis chuck or something like that. So the reason is I grounded my 12 volt power supply ground, which is also the same node as this magnet wire. I grounded that to my CNC chassis. So back inside my box, I connected that to the sheet metal of the control box, which is also all electric connected, because that's your safety ground for the system. So all the chassis, all your gantry, my laser chassis, the spindle body, that's all grounded. And if your spindle has good electrical connections from the spindle body to the shaft, then you've got that path to the chassis already made, and you don't need this magnet wire if you've grounded the 12 volt ground to chassis. And so I've verified that I have the 4 horsepower Hiteco. I'm pretty sure the 8 horsepower one does it as well, and I'm pretty sure the old AVID 3 horsepower spindle does this as well. Now I know some of them don't. I've heard some people say the CNC Depot, some of the CNC Depot spindles don't conduct into the shaft very well, so they do need a connection to the actual shaft directly or to the bit, so this magnet is needed. So you have to verify that on your spindle itself. I talked to AVID once, and they measured several of the spindles that they had in stock, and they all have consistent connections. So the Hitecos are good for this. So this is very convenient. You don't need to drag this magnet wire. You can cut it off, or you just put it aside or whatever if you want. wrap it up and zip tie it to the side of your main cable. You just don't want to electrically connect it to this, but that is a little bit of a time saver. The one risk with that is potentially sometimes the chassis ground could have a decent amount of noise on it. If for example, your shop wiring isn't done very well and you've got some grounding problems, you could have a lot of 60 or 50 hertz power noise on that chassis. And by connecting the ground to the 12 volt supply, then you'd be essentially injecting noise into your whole 12 volt system. I did verify that on mine with an oscilloscope. It didn't impact things significantly. On an Avid, that 12 volt supply is used for all of your sensors, essentially, like the proximity sensors and stuff. It is isolated from your 5 volts and your 48 volts, so it's not going to go too far. But most people, I haven't heard of anybody having problems with this, putting this short on there, as long as their spindle works with that. So anyway, that's that. Let's go into some of the tips on where to do the wiring. So on this page, we've got the pinout here of the M12 sensor input. So you could just drill holes in your control box and run a wire and everything, but that's kind of messy. I like to. It's nicer to do it a little more robust so that your wiring stays solid and everything over the years while you're using it. So I really like the M12 sensor cables that Avid supplies with the machines. You can buy them, and the bulkhead connector, the female side of it that goes through the control box. Both of those you can buy from Avid on their site. So I just bought one of each and drilled an extra hole in the bottom for the bulkhead, and then ran the cable in to that bulkhead connector. And then I'll show out on the other end up at the spindle, I just cut it off and soldered on the connector that goes to the probe itself. But these wires are shielded, they're twisted pairs, so they're very immune to noise and stuff. So the two wires that, we'll go back to this, these two wires, the 12 volt supply and the ground, those are easy to pick up because those literally can go to the 12 volt power supply inside the control box. So you can just put those into the screw terminals with the other two wires that come out that go to the CRP 850 board. The only tricky one is the body here. This is a particular output signal from the CR 850 board. So if I go back to this page, on my CRP 850, I have the old revision 17.4 of the control electronics, and on that board, that was a dual wired signal, so it actually came out to pin 9. So if you have that one, it's very convenient. You just hook it up to pin 9. So essentially, you get a wire from your 12 volt supply, you put a 2.4K resistor on it, and then connect that to your input. And then on the other side, on the output side of this board, this will go to the 12 volt supply, and then this wire is just going to go to that board straight from that pin 9. But if you don't have that board, this is kind of buried. It goes through a ribbon cable to this connector between the 860 board and 850 board. There's not a really easy place to intercept it inside the box. So then what's a pretty easy thing to do is you can, and there's a link right here for one I saw on Amazon, but there's tons of these. Basically, it's an M12 splitter so that you can plug, it would have one male end that would go up into the existing connection coming out of the bulkhead for the probe, and then the existing Avid probe would plug into one of those two outputs, and then you would plug in a new cable and then put a bulkhead connection in your bulkhead like I did. So drill another hole and put a bulkhead M12 connector in there and just have that come right back into the box. So you're basically splitting it outside the box, and then one of those connections you're going to bring back into the box, and then one of them is going to go to your normal AVID probe. And on the bulkhead connector, these are the two wires, the light blue one. So the 12 volt normally connected, ground, and normally open connections. This is the standard wiring for an M12 sensor. That's not how the touch probe is, because it's not a sensor in that there's no 12 volts, and these two aren't connected to anything. The magnet wire is the light blue wire, and the black wire is the touch plate body wire. So those are the two that you need to connect. So the light blue one is going to go to your ground, to your 12 volt ground, and then this black one's going to go to the either pin 9 if you have my style, or the it's going to get picked up by the one that goes to the splitter with the standard. You want a standard M12 connection there. Of course, you'll have to test that and make sure that they follow the same wiring standard as this one is. And if it's not, you might have to rearrange which two pins you use, but this is the way mine was. So anyway, that's two ways to do this pretty easily without like cutting into your AVID cable. I mean, yeah, you could obviously cut into your AVID touch plate cable if you wanted, but that's a little gross. If you use a splitter or use this internal connection on the 850 board, it's a lot cleaner. So that's the basic wiring and theory of operation of how it works. Let's go take a look at the actual physical wiring in the box now.
I've already covered the detailed wiring, block diagrams and stuff in the video. Now I'm just going to show physically what it looks like. The other thing I wanted to show is the indicator here. You can see, so that's the indicator I was talking about. It's got a nice little blue LED when it's tripped, so it's kind of a nice feature. I can point it towards my operation station on my computer and see that it's probing correctly and where it's tripped. So let's take a look at the wiring and stuff. So what I did was I bought a standard AVID M12 sensor cable, so it's the same kind that's on the sensors here, and I just cut the end off and then I wired it into the cable that came with the probe. So that's all I have up on this side. And then that goes down into my cabinet, so we'll take a look at that next. Okay, just to show what I did here to bring things in. So underneath here, this is the new bulkhead connector that I added. And you can see it's the top side of it's down here. So I bought that from AVID, and then I bought the cable for it from AVID, which is the same as the touch probe cable or any of the other sensor cables I have. So that's where in here I talked about this, or in the schematic section this is the little driver board. It's a open collector or open drain pull down driver, essentially, to short out the line. Here's the ground wire I talked about for creating essentially, so you don't need to use the magnet wire anymore. I basically, you can see I just grounded the loop right to the connector here for one of the motors, and then that goes into up to the 12 volt power supply up here. So that's your 12 volt power supply ground, and then I bring this red wire as the 12 volt power to come down. There's a resistor in here underneath, that 2.4 k ohm resistor is underneath this heat shrink, and then that is what goes to the input of this board, and the other wire goes to the probe, which is this one here. So this is going down to the probe, and then the black wire that comes back is the ground from the probe, and that's going to the ground of this here. So it's pretty simple wiring. I know this looks like a rat's nest. My CNC is more of a platform for playing around with electronics and testing new tools than anything else. So I've rewired this one a lot of times. This is the little relay board. It's a solid state relay, but it's a relay board to run the reverse for my spindle. This here board is the AVID breakout board for laser stuff, and you can see I used most of the outputs and inputs on it already. But the additions for this probe are pretty simple. Back here, I don't know if you can see that back behind there, that this black wire back here, that's the one I talked about that goes to pin 9 of the CRP 850 board. Again, my board is an older revision that has that. And when I was talking about putting a splitter on, if you have the newer versions, you would basically just put a splitter down there back in, way in the back here is the existing probe connection. You would hook the probe to one of those outputs, and then the other one would come up into your bulkhead connector here. And so you would basically just intercept the probe signals between the existing cable and the bulkhead connector, and then bring it into a new bulkhead connector here for your second connection, so you can hook up your device here to run off of the shorting probe or the normally closed probe. So that's all the location stuff I had. If you have any questions, feel free to send me a comment or question in there, or email me if you need some help, or if you have a slightly different thing in mind that you want to do, I can always help there. All right, that's it for everything. Like I said, this was just going to be a hardware kind of connection overview. I'll get to reviewing the probe itself when I get the software up and working, so I can do a lot of repeatability testing to see how accurate and repeatable it is, and just find out how useful the whole thing turned out to be. Didn't really cost much, it's a couple $100 for that probe, and the rest of it's just a few wires and stuff. So it's a pretty simple addition, and I think I'm gonna really like this drop down probe location, but time will tell there too. So that's it. If you have any questions or comments, let me know. Thank you.